Good afternoon. We're going to see today, in the second lecture, I'm going to give a brief introduction to deep learning. That part will be a bit extra, but now for the last part of the subject matter you will be tested on, we will look at probabilistic models. So basically, I'm going to talk about probabilistic clustering, which is another approach to clustering where we use we compute probabilities of each example belonging to different clusters or being generated from different distributions. We're also going to see graphical models. This is a way or different ways of representing relationships between random variables or between variables so that we can model some problem by the relations of these variables. And then for one kind of processes that we can model, we're going to look at Markov processes, which are stochastic processes, and hidden Markov models. These hidden Markov models are very used in analysis of sequential data. It can be, for example, temporal series. It can be sequences like in genes or text or things like that. So we're going to look at these hidden Markov models. In this lecture, the equations will be even a bit uglier than in many previous lectures, but we won't focus so much on the details of the equations. This is just to get an idea of these methods. So let's start with probabilistic clustering. Suppose that we have a probabilistic model for the distribution of our examples. So X there is the set of features for each example and the set of all examples. And also we have this Y, which we know where each example belongs to. So different groups, and we have some model for the probabilities, the joint probability of X and Y, which we can also rewrite as the conditional probability of X given Y. So if we know the group where some X comes from, an example comes from, we know the probability distribution of those examples. So this not only would give us a way of grouping the examples, because we know why, we know where they are grouped, but also we would have a way of generating new examples. Because if we know the probability distribution of examples from each group, we could generate new examples by sampling from those probability distributions. So this is basically what we had with naive Bayes, where we had a probabilistic model that, depending on the classes, the features had different distributions, and we could generate new examples of the same kind, assuming that conditional independence and so on. That was part of the naive Bayes model. The problem with clustering is that we don't know why. So we can think of clustering as something similar to classification, but instead of knowing which category our training set belongs to, we do not observe these class labels, and these are hidden variables in our model. So instead of this, what we have, we saw this for clustering. We saw this problem when we looked at the first examples like expectation-maximization with k-means. And the idea is that we observe the features, so we have all our examples, we can observe the features, but we don't know which group each example belongs to. So instead of calling it Y, which is an observed class, we call it Z, which is a set of hidden variables that assign examples to different groups. We also have some parameters for our model. For example, this could be the centroids of our clusters or something like that. And we need to figure out how to optimize the parameters. But instead of just having to optimize the parameters, knowing everything else, we also don't know which cluster each example belongs to. So let's suppose that these probability distributions that of the examples belonging to some category, which we don't know in this case, would be group Z. But if we knew from which distribution the example came from, Let's suppose that the distributions are Gaussian. So each distribution is a Gaussian curve. It has these two parameters. So this is a scaling factor depending on the standard deviation, but we have the standard deviation there and the mean, and this will determine the shape and position of the curve. If we have in one dimension, it would have this formula. So this is the familiar Gaussian curve, and we could consider some distribution by mixing together different curves. So we could create a linear combination of different Gaussian curves and use that to create a distribution with some shape that we want. Each example would come from each of those different distributions, but when we add everything together, we get a cloud, a shape depending on the mixture of the different Gaussian curves. Of course, this would be for one dimension. We would have those parameters for the Gaussian distributions. If we consider in more than one dimension, this becomes a bit more complex because now instead of having one value for the standard deviation, we actually have a covariance matrix that not only gives us the variance in each axis, but also the relations between the different variables, the different features, so to speak. So actually, these shapes, if you imagine them, for example, in two dimensions where the height is the third dimension, they could be on the diagonal, they can be symmetrical, they can have different shapes, and this sigma here would be the matrix that determines that shape. But the general idea is the same. We have Gaussian distributions in n dimensions. These n dimensions are the number of features that we have. And the parameters for each Gaussian distribution is the mean point, the center of the distribution, and that sigma, the covariance matrix that determines the shape of the Gaussian. So we can define a mixture of Gaussians that would give us the probability of an x appearing at some point as the sum of different Gaussian curves with different parameters, each one multiplied by a fractional value, so that the sum of all these pi values, all these fractions, adds up to 1. So we are creating a probability distribution that is the sum of different Gaussians with different weights, in a way that all the weights summed up add up to 1, so the total probability is 1, which is a requirement for being a probability. So this is our model for clustering examples with this type of probabilistic clustering. This is called a Gaussian mixture model because we are mixing together different Gaussian distributions. So let's consider that we have this variable z, which for each example, we have the variable is distributed in a way that it can be 0 for all classes, all those Gaussian curves except one, and it's 1 for one of them. So the values of z are either 0 or 1, and when we add all the values of z for one example, they add up to 1. So what we represent in this way is which Gaussian distribution that example comes from. So each example will come from one of the Gaussian distributions in the mixture. So these are the latent variables, the hidden variables in our model that assign each example to each cluster. The marginal probability of z, of one of the z's being 1, that is the probability over all possible data samples, will be simply phi. So the probability on average of z for class 1 being 1 is the fraction of Gaussian number 1 in our mixture. So if we have more component, more contribution of some particular distribution, then it will be more probable that points come from there and vice versa. So now we have this probability of x as a function of our hidden variables, and we can also compute the probability of x of a point being in some specific place by adding the contributions of the different Gaussian curves. So this is basically the idea here, is that we sum all the Gaussian curves, each one with its own weight, and that sum gives us the probability of each particular value of our features. Now, the question is, how can we compute this, the parameters for these distributions? Because we have a fixed number of distributions, but they can have any mean points and their covariances, and we need to compute that. So let's consider here the probability given some x that this point belongs to one particular class. So this is basically the clustering problem. We want to figure out for each example which Gaussian curve it came from. We want to assign it to one of the groups. So we can write this, the probability, the marginal probability of belonging to that example, and the conditional probability of x, of having those features, if it came from that distribution, and then we divide that by the sum over all different Gaussians. Okay. So basically, we can compute the probability of x belonging to any particular Gaussian curve by the probability of that x from each Gaussian curve divided by the sum over all the Gaussian distributions that are contributing to the mixture. We'll call this ratio gamma. So this is easy if we have the parameters, because we can compute how probable it is for each distribution to generate a point in one specific place. And so if we have a point in a particular place, we can compute the ratios of the different probabilities and see the probability that it came from any given distribution. But we can only do this if we have those values. So basically, we can write we want to maximize the likelihood of our parameters. For that, we need to assign the examples to different Gaussian curves. But for that, we need to have the parameters. So you see, we have a similar problem to what we saw in k-means, which is we need to know where the centroids are to assign the points, but we also need to know which points belong to each centroid to compute the position of the centroid. So we can, if we have this function, the likelihood of our parameters, we can compute the derivatives at 0. So this is basically the maximum likelihood solution. I'm not going to spend too much time here, but we can use these gamma values, the probability of belonging to each cluster, as a weight for each example, and then use that to compute the minimum, the central point of the Gaussian curve that generates that cluster. So basically, we assign the mean point of the Gaussian curve depending on how likely each point is coming from that Gaussian curve, and we use that as the weight to center the Gaussian curve. And we can do that for all the components of our Gaussian mixture. The same thing for the covariance matrix. We can compute the covariance matrix by using the difference between each point and the central point of that Gaussian distribution, but then each point contributes to that sum according to the probability of belonging to that Gaussian distribution, or having come from that Gaussian distribution. So if we have this function, we can compute the best values for our parameters as a function of the probability of belonging to a Gaussian distribution. However, we can only compute the probability of a point belonging to some Gaussian distribution if we already have the parameters for the Gaussian distribution. So this is where expectation maximization comes from. We start with one initial guess for the parameters of our Gaussian distributions and the mixture of Gaussians, and we can use that initial estimate to compute the expected value of those probabilities of each point belonging to a particular Gaussian. Once we have that expectation step, we now can write the likelihood function, because we already have those gamma values, those probabilities of z, so those gamma values for all the points. And now we can compute the optimum value for our parameters. Of course, once we compute the optimum value for our parameters, assuming that probability distribution of the points belonging to different Gaussians, now that probability will change and we'll have to go back and recompute the estimate assignment of the points to the different distributions. So basically this is the expectation maximization algorithm when applied to probabilistic clustering, where we are actually dealing with the probabilities. We compute the probability of each point belonging to each Gaussian curve, and then from there we compute the optimal parameters for all the different Gaussians, assuming that probability of each point having come from each of the curves. And then we recompute the probabilities of the points belonging to the different groups and keep doing that until it converges. So to illustrate, suppose that we start with these clouds of points and we are trying to cluster them with a mixture of two Gaussian components. After the first iteration, we have these distributions here, the blue one and the red one. So these represent the sizes of the Gaussian curves. But then this one gets a bit narrower and we eventually converge to something like this. Of course, those points seem to be distributed in 3 clusters and not 2, so we can get better results if we use 3 components, but the idea is the same. We start with an initial guess, we assign the points, compute the parameters for the distributions, and then repeat until it converges so that across different iterations the differences are very small and eventually we stop. So this is an example of probabilistic clustering using a mixture of Gaussian distributions, and this is actually the application of expectation maximization. So you can see this as a probabilistic version of what we did with k-means, for example, where we were not actually applying expectation maximization because there were no probabilities, but it was a similar kind of problem where we had to iterate by estimating the hidden variables and then using that estimate to optimize the parameters and going back and forth. So with scikit-learn you can use Gaussian mixtures with this class here, Gaussian mixture, and you can set the number of components. These are the number of Gaussian distributions that we're going to add together. The type of covariance, these are constraints on the covariance matrix, whether they can be symmetrical or equal to all sizes or having no constraints at all. So you'll have different options there. This is the maximum number of iterations. If it does not converge up to that number of iterations, the algorithm will stop. And then you have different attributes if you want to see the weight of each Gaussian distribution, and then the means and the covariance matrix for each Gaussian distribution. So if you want to see the parameters of the Gaussians inside after training this clustering object. So this was for probabilistic clustering. Now let's look a bit more general when we're trying to model something that has probabilities. And one way of doing that is to use a graphical representation of how the different variables are related. We're going to look at Bayesian networks and Markov random fields, which try to represent different things, and we're going to see some examples of Markov random fields, and then we're going to look at a particular case of Bayesian networks, which are dynamic Bayesian networks, where we try to represent evolution over time too. So this is the idea of using a graphical representation in Bayesian networks. We use a graphical representation to represent the joint probability of a set of random variables as a function of conditional probabilities. So basically we have this graph here where each node represents one random variable and each arc represents a conditional dependency. We can also add things like we can have a shaded node if it's a variable that we observe, that we know what the value is. We can add parameters that are not random variables and so on. But in general, the idea is that we have parents and offsprings an offspring depending on the directions of these arrows. These arrows represent conditional dependency, and the graph itself must be acyclic. We cannot have loops inside this graph, because what we're trying to represent here is ways of factorizing the joint probability of the variables depending on, based on their conditional probability. For example, if these variables are all interrelated, we can write the joint probability of A, B, and C with the probability of C given A and B, so the conditional probability of C given A and B, multiplied by the conditional probability of B given A, and then multiplied by the marginal probability of A. So we could represent the joint probability is the same as that product, and this would imply that C is somehow dependent on A and B, B is dependent on A, and A is independent of the rest. So we are creating here a dependency graph of the probabilities of the different variables. Of course, the same set of variables can be factorized in a different way. So we could write the joint probability of A, B, and C in this way, with C being dependent on A and B, and so on. Or we could do it, for example, this way, where A is dependent on B and C, B is dependent on C, and C is the independent variable. So there are different ways of representing the joint probability of these variables. But, yes?
Do you think that we can conclude with this representation is the dependency?
Yes, we are representing conditional dependencies of the variable.
The only thing that looking at this graph we can conclude.
Well, conclude, we can compute then the probabilities and so on. Yes, but what we're trying to represent is something of this sort. So the probability of the grass being wet depends on whether or not we turned on the sprinklers and on whether or not it rained. Now, turning on the sprinklers can depend on the probability of having rained or not, because if it's raining, we are not going to waste water watering the grass. But rain does not depend on what we do with the sprinklers. So we could represent these causal relations by saying that rain is independent of the rest. The grass being wet depends on both other variables, and the sprinkler will depend on whether it's raining or not. So we could use Bayesian networks to model relations between variables where the probability of one will depend on others. So this is one use of Bayesian networks. And once we have the graph of dependencies, we can compute the expression for the joint probabilities by, for each variable, we have the probability of that variable conditioned on the parent. And now we're going to compute the joint probability over all the variables by simply multiplying these conditional probabilities. For example, this is an example taken from Bishop's book. We can see here that the joint probability of these 7 variables will be the probability of x1. This one does not depend on anything. Then the probability of x4, x2 and x3 also do not depend on anything. Then x4 depends on x2, x1, and x3. So x4 depends on the joint distribution of x1, x2, and x3. x5 depends on x1 and x3, and so forth. So we can, by multiplying all of these, we can get the expression for the joint probability. Note that this was something that we did with naive Bayes. So we determined that each feature was conditionally dependent on the class, and so we computed this as each feature was conditioned on the class, and we just multiply all those conditional probabilities and then multiply the prior probability of belonging to the class. Okay. So it's a diagram of this kind where each feature is conditionally dependent on the class, and we can represent a naive Bayes classifier in that way. So a different way of representing relations between random variables is to use Markov random fields. In this case, what we are representing in the graph is conditional independence. That is, we are saying that these variables here are independent of these ones if we know those in between. So the idea we're trying to represent is that there may be information about different variables that are related in this graph, but if we cover all the paths between them by something that we observe, then there is nothing new that we can learn about what goes on in one side that would inform us about the rest. So basically, we are representing here that if we observe this part, then nothing that happens here will inform us about that other side of the graph beyond what we already know by observing this part. So this is a way where this is harder to do with Bayesian networks because the direction of the dependencies makes this conditional independence harder to model. But with Markov random fields, we create a graph that has a set of random variables and arcs connecting them. And basically, if all paths between between a set of variables u and a set of variables v go through a set of variables that have been observed, then u and v will become independent. We can consider that they are independent from each other. There are some consequences of this. For example, each node in the graph is independent from everything else if we observe all its neighbors. So if we look at all the values of the neighbors, then the node is no longer dependent on anything else outside. Also, if we choose one particular group and select all the neighborhoods, that group will also be independent of everything else, and so on. So what's the use of this? With these properties, so if the groups are independent of other groups once we observe all the paths, we can represent the joint probability distribution by looking simply at the cliques. So a clique is a set of nodes that are all interconnected. So each node in the clique has a direct connection to all other nodes in the clique. And we can represent the joint probability distribution over all the variables by simply multiplying the maximal cliques. So we take the maximal cliques, some function of those variables in the clique, and we compute the product of all those functions, of probability functions, and we get the probability distribution for all the variables. So this is an example. We have these 5 variables here, but we can consider these cliques. 6 and 4 form a clique, 4 and 3, 4 and 5, 5 and 2, and 5, 2, 1 also form cliques. If we compute the probability distributions or some function representing those distributions for each of those cliques, then the joint probability distribution of the whole set is simply the product of those smaller probability distributions. The advantage of this is that, if you recall from the lecture on naive Bayes, is that if we have a large number of variables and we don't have any constraint on the joint probability distribution, we need to look at all the combinations of values to get an idea of their joint probability distribution. If we break it down into small groups, the number of combinations reduces a lot, and it makes it much easier to do these computations. So this would be a way of using the Markov random fields. An example for this is for denoising images. So imagine that we have this image that has lots of noise, and we can clean it up a bit and obtain that image with less noise. And we can do this with a Markov random field that has an array, a matrix of variables, x. These variables can be -1 or 1, and each variable x represents a pixel on the true image, so the target image that we want to obtain after removing noise. And we have these variables y that we observe that represent the noisy image. So y would be this image. Each variable y can also have a -1 or 1, depending on whether the pixel is blue or yellow. And we have this observation, and now we want to compute what is the most likely distribution of values in the true image that generated this random image. So the generation of each pixel in the noisy image depends solely on the true value for that pixel. But we can also consider that the true value of each pixel will also depend on the values of its neighbors, because there are lots of regions here where the color is uniform, so each pixel, the probability of being 0 or -1 or 1 will depend on the values of the neighbors. So how can we do this? We can create this sort of energy function. So this is often based on the Boltzmann distributions, and the Boltzmann distribution, which basically relates the probability of the system being in a state with the energy of that state. So we can write functions about the probability thinking in terms of some energy that we want to minimize. So we can create this energy term between neighboring values of x. So this would be pixels on the true image, which is this minus some scaling factor and the sum of the neighboring of the products of the neighboring pixels. So each one can be -1 or 1. So if they have different signs, we get a negative value there, and with the negative that we have here, this increases the energy. It becomes positive and makes it the energy increase, so it reduces the probability. If the pixels have the same sign, then the opposite occurs and it decreases the energy. We can do the same thing for the x and y relations here, where the sign of the pixel that we observe in the output image is the same as the corresponding pixel in the true image. And also we can set a bias, a prior probability of pixels being in value 1. So if we do this and then we minimize the energy, note that now these joint probability distributions of x and y, even though we have a very large number of pixels, so if we didn't have any constraints about their probability distributions, this would be a terrible problem to solve because of all the possible combinations. Given that we can represent this with this random Markov field, we only have to concern ourselves with these cliques. So neighboring pixels in the true image and the relation between the true pixel and the noisy pixel in the image that we are seeing. So when we minimize that energy, we get this result, because now we are favoring the neighboring values to have the same sign, to have the same value for the pixel. So all these small dots that are incorrect, most of them get fixed in this way. So these are two ways of representing random variables and their relations. And the big difference is that with Bayesian networks, we represent these conditional dependencies, and we can create a graph that represents some knowledge, so to speak, about which variable influences which variable. So it's good for those kinds of things that we cannot represent with random Markov fields, but they make it more complicated to try to isolate independent parts of the graph. With random Markov fields, we don't have this notion of direction, so we can even represent loops and so on. But they are mostly to try to represent which parts of which subgroups of variables we can separate as independent to decompose the computation of the joint probability distribution. So basically you have two different ways of trying to represent graphically the relationship between random variables. From these, then, we can extract the expressions for the probability distributions, and we can use them to solve problems, to compute the most likely configurations, and so forth. Now, one thing we can we also represent with Bayesian networks is this dynamic Bayesian networks, which is an evolution of some variable over time. So this would be a simple representation of a Markov process. A Markov random process is a sequence of random events where the probability of each event depends solely on what happened immediately before. So, for example, think about the Monopoly game. The probability of reaching some particular location in the next turn depends solely on the location you're at on this turn. It does not depend on what happened in the past, because it only depends on on which street you're at now, and that the roll of the dice will determine the next street from here. But we can think about Markov processes as modeling many different types of processes, depending on how large the step we consider to be. For example, if you consider the weather in increments of 1 month or something like that, then probably the weather this month will depend mostly on the weather last month and not the weather 2 months ago. If you consider, for example, trying to model text, words in the text, you can look at what happened in the previous sentence, but probably it's not very relevant to look at larger distances before. The same thing for genes, for processing sound files and so forth. So this kind of process, Markov processes, can be used to model a lot of different temporal sequences. And one particularly useful model based on Markov process is the hidden Markov model. A hidden Markov model can be represented in this way. So this is a time series. You can think of it as a sequence where there is a hidden state. We are calling this X. We cannot observe it directly. And from one time step to another, the state can change with some probability distribution. So depending on the state we are at here, we can go to a different state here, and then depending on this one, there will be a probability for other states and so forth. Furthermore, aside from these hidden states, there is also, for each state, a probability of emitting these Y values that we can observe. So let's say the hidden state is something the person is thinking, and it's changing from time to time, and the observable is what the person is saying, which is a function of what they're thinking. There may be some probability relation there, but we can also see hear what the person is saying. We cannot see what they're thinking, but what they're thinking is changing, and we can follow more or less we can follow the sequence of observables and maybe make some inference about the hidden states if we have some model for that. In fact, this kind of thing is also used for communications. For example, when you have limited bandwidth, for example, in phone, the analog phone lines, where we only have about 3 kilohertz for the carrier, and you need to put several conversations in the same wire, you can use convolution and then use this kind of models to try to infer for each one which is the actual sign, which is the actual state or the bit for each of those communications. So the hidden Markov models are used for lots of different things like speech synthesis, recognition, identification of speakers, bioinformatics. Even in Wi-Fi communications, you have these kinds of algorithms to try to disentangle the actual state from mixed communications, for example. So one way of representing this is not a Bayesian network representation. I'm just representing 3 different states. They have different probabilities of transition from one to the other, and then each state can have different probabilities of emitting particular symbols. So this is the abstract conception of hidden Markov models. What we need is, if we have n possible states for the hidden states, then we need an n by n matrix that gives us the probability of transition from each state to a different state in the next time step. Note that not all the parameters are independent, because these are probabilities, so the rows and columns must add up to 1. There is some interdependency, but we need basically those n by n values to know what is the probability of some state in time t becoming each of the other states in time t plus 1. Also, we need the probabilities of emitting the observable symbols. So if you have k different values that can be observed, we need a k by n matrix so that we know for each state what is the probability of each value being emitted. So in this representation, this would be the transitions between different states, an n by n matrix with all these values, and with these k equals 4 symbols being emitted, we would need a 3 by 4 matrix to have the probabilities of these emissions for each of the states. And finally, we need to start our process, so we need to know the probabilities for the initial state. And we have basically, we have n possible states, so we have n minus 1 independent parameters because the one left over is simply the difference to the total of 1. The probability must add up to 1. So, probabilities of transition between states, the probabilities of emitting symbols depending on the state, and the probability of starting in any of the possible states. So what can we do with this? One thing that we can do is to try to recognize different patterns by looking at the sequences, for example, of the hidden states based on what we observe. We can do that to tag text, to try to convert, to interpret sounds, voice recognition, and so on. This is also done for, in bioinformatics, for example, for trying to determine if we are at a region of a gene that is coding for a protein, that it has to stop, that has a break, that is a regulator, that is an intron that's going to be thrown away, and so forth. And these are hidden states because we cannot observe them directly, but we can observe the actual sequence and we can compute the probabilities based on those observations. So one thing, this is called filtering or computing the belief state, is to compute the probability of each state at time t and the observations up to that state. So this is also a way of computing the likelihood of a sequence of observations. Now, if you think about this model, each observation comes with different probabilities from different states. The states can also change from one to the other with different probabilities. So computing the probability of a given sequence of observations here would naively require us to consider all the combinations of hidden states in order to add up and to marginalize that for the sequence of observations. However, since this is a Markov process and each state depends only on the previous one, and we can ignore everything in the past from there, we can do this more efficiently by doing this recursively. So basically, we can consider the probability of the state at the beginning given that particular observation, so the first observation, as the conditional probability of that observation having come from each of the states, and multiplied by the prior probability of our sequence starting in that state. So this pi is one of the parameters we have here, which are the probabilities of starting in a particular state. So for the first state, we have some observation, and we can compute the probabilities of being in different states by considering the observation and the prior probability of having of starting in that state. And then we can do it. We can follow each time step by considering the probability of transition, so the probability of having some particular state at time t based on the state at times t minus 1, and the probability of the observations and the state being at time t, t minus 1, considering all the previous observations. So we are taking advantage of the fact that Markov process does not have a long memory, it only remembers the last step, to do this incrementally, and we don't need to compute all the different combinations. Another thing that we can compute, which is a bit different, is the most likely sequence. This is actually, this Vitterbi algorithm is used in telecommunications to try to deconvolute messages that were convoluted for using the same carrier, or deal with problems like noise and things like that. So basically what we need to compute here are two matrices. They have, you can imagine, one row for each possible state, one column for each time step. And now, in one matrix, we're going to compute the state of the probability of the state for the most likely path up to that particular state. And we can do this in a similar way by doing this incrementally, starting from the beginning. So basically, we have the distribution of the starting states and given what we observe, and then we do it incrementally from the previous state. And also in the other matrix, we are going to remember for each state what would be the previous state of the most likely path. Once we compute those metrics, we can trace the path back, and this gives us the most likely sequence of hidden states that would produce what we have observed. So basically, again, this would be something that would require looking at all the different combinations, unless we take advantage of the fact that this is a Markov process, and so it only has a memory of one step. So we are always computing things based solely on what happened in the step before. So what can we do with this? Some things, for example, in bioinformatics, we can, given the sequence of the gene, try to find the most likely sequence of some hidden states that we have in the model. For example, what different parts of the gene are doing, like regulators and introns, exons, and so on. We can also do this for speech recognition, for if we have hidden states about different parts of what the words are being said. Because if you look at the sound, you can think of the sound as something that you observe, and the actual word that is being uttered as a hidden state in your model. And then you try from all the sound waves that you got, what is the most likely sequence of words. Note that this has the advantage that you're not only considering the probability of some sound being related to a word, but also the probabilities of words following each other, because those hidden states also have transition probabilities. And so even if it seems like the person is saying one word because it sounds like that, but that word is very unlikely, your system can correct and use a more likely word in that place. Note that there is although they seem similar by the way we compute, the forward algorithm basically asks what is the likelihood of a sequence of observations. You're not actually computing what is the sequence of hidden states, whereas the Vitterbi algorithm serves to compute what is the most likely sequence of hidden states given some observation. Okay, so all of this we can do if we know the probabilities of transition, the probabilities of emission, but we need to obtain those in some way. So this is, we can use the Baum-Welch algorithm to train the hidden Markov model. If we have a large set of examples, I'm not going to go into much detail on the equations, but the idea is that we don't know the transitions and the emissions in our the probabilities of transition and emission, and we need to compute those. But we can try to estimate the probabilities of each point, each state at each time, being some particular state, given all our observations, and the probabilities of transition, probabilities of emission, and the probabilities of starting at a particular state. So if we knew what the parameters for the model, we could not only compute the probability of each state given the observations, but also the probability of going from one state to the other given the observations. So basically, how can we compute this? We don't need to look at all the possible combinations. That would be prohibitive. But we can take advantage of this incremental nature of the Markov process by computing these terms, which is the probability of having each particular state at times t based on all the previous and the joint probability of that and all the previous observations, depending on the parameters of our model. And also, and this can be done starting from t equals 1 and doing incrementally. And we can also do it the other way around. We can compute the probabilities of all the sequence of future observations given the state that we are currently in, and also the parameters of our model. So these two things we can do incrementally, one starting from the end, from the last observation, the other starting from the beginning, and this is the forward path and backward path. And in one case we are always looking for the previous state, the other case we are always looking at the next state and going backwards. And with these two we can now do these computations. We can compute the probability of each state at each time and the probability of the joint probabilities of two states in consecutive instances. Now the problem is that to do this, to compute this, we need the parameters for our model. So if we don't have the parameters for our model, we cannot compute this. But if we can compute this, we can compute the parameters for our models, because if we know the probability of the state being in some particular state at some time, and we know the observation at that time, then we can compute the emission probabilities when we average over all the observations we are making. And also we can compute the transitions if we know the probability of two states occurring in sequence, and also the probability or the number of times each state occurs. So we can basically compute the matrices that we need from those values. The problem is that we can only compute these values if we already have the matrices of transition and emission probability. So this is once again expectation maximization. We start with some guess for all those transitions and emissions. We use that to compute those probabilities, the joint probabilities of hidden states and emissions, and the joint probabilities of consecutive hidden states. So we do this with the forward and backward path, assuming some set of parameters. And now from these probabilities, we can compute a better set of parameters. And we iterate this, and we do this until convergence. In this case of expectation maximization, there is no guarantee that we'll get the optimum result, but usually this works, although of course we always have these problems of overfitting and so on if we have too many parameters for the data that we have, but we can create the hidden Markov model in this way from the data. So hidden Markov models are also generative. We can use them for classification, for example, by computing probabilities. This is one way of sorting protein sequences in families, for example. Given a set of hidden Markov models that describe families of proteins, for a new sequence we can figure out which one in those sets has a high enough probability of generating a sequence like the one we have, and so we can assign it to one category. But we can also use the hidden Markov model. We can just run it with the probabilities and generate new data using that model. So you can do that, for example, for speech synthesis and things like that, or text. There are some text generators online that are based on hidden Markov models that you can just click a button and it generates something that was trained, for example, with Harry Potter and looks like a Harry Potter story, or with postmodernist papers that looks like a postmodernist mumble jumble and things like that. So you can create the model, train it from a sample, and it generates similar things from that. So to sum up this part, the important things here in this case are not so much the equations, so I just leave them for reference, but to get this idea of especially expectation maximization, how we can use it in these kinds of unsupervised learning problems. We usually need to find a set of parameters from which we can compute probabilities of something, for example, the sequence of states in a hidden Markov model, or the probability of a point belonging to some cluster in probabilistic clustering, but we need the parameters to compute those probabilities. On the other hand, we don't have the parameters initially, so we need to guess the parameters of our model, use that to compute the probabilities of, say, assigning some values to the model, or the probabilities of transitions and emissions in a hidden Markov model. And then we do this iteratively by creating this expected function from the initial guess of parameters, and then optimizing that function or maximizing that function to get a new, better set of parameters. And we do that until convergence. We also saw this idea of graphical models, so how we can represent the relations between random variables and in different ways depending on what we want to capture. So with Bayesian networks we capture conditional dependency. In random Markov fields we try to capture the groups that are independent from each other. And also these algorithms, so basically Baum-Welch for training hidden Markov model and Vitterbi for finding the best or the most likely sequence of hidden states. So you can see in these sections on Bishop if you want to read this more in detail.